Hi everyone, I'm Stephen, and I'm a computer scientist at the University of Kentucky, where I run the Narrative Intelligence Lab and do research on AI for interactive storytelling in games. I've always wanted to attend Roguelike Celebration, so I'm really excited to be here for my first time. Today I'm doing a quick and partial history of storytelling algorithms. That history starts in 1976 with James Meehan's Tailspin. Since then, a lot of people have asked, can you get a computer to write a story for you? Though I'd argue that's not really a very interesting question. The world is full of people who want to tell stories. We don't need computers to replace them. The more interesting question is, can you get a computer to rewrite a story for you? Writing a story is fun, but if you put it in a game and make the player one of your characters, you have to be ready to adapt your story around them. We know this can be done. People do it all the time when playing games like D&D, but when your story's in a video game and you don't have a DM around to rewrite it, you need some kind of algorithm. So I'm going to talk a little bit about how we've tried to represent a story on a computer and whether we can automatically rewrite stories fast enough to be useful. This talk is specifically about the history of automated, planned, event-level interactive narratives. I'll explain what all that means, and by extension, I'll define all the cool stuff this talk isn't going to cover. If you're into games, you're already familiar with the difference between static narratives, like books and film, and interactive narratives. You've got a story that involves a player you don't control who's going to make unexpected choices that you have to adapt to. One way to classify storytelling algorithms is by what they consider an atomic unit of story content. Some of the earliest successful interactive stories worked at the scene level. Facade, for example, has this library of short scenes that might involve several small conversations and choices, and the AI is trying to decide which scene to show you next. A scene is roughly a paragraph of content in a written story. These days, large language models can write stories one token, which means basically one word at a time. The algorithms I'm talking about today are at the event level. An event corresponds to about one sentence with a subject, verb, and direct object. If you've ever played a Scum-style adventure game, that's an event-level narrative. You can also think of it like the difference between IKEA furniture, Lego bricks, and a 3D printer. We are working with the Lego bricks. When I say planned stories, I'm contrasting them to emergent stories. Games like Dwarf Fortress and The Sims have a virtual world populated by many relatively lightweight agents, and all sorts of funny things happen when you wind them up and let them loose. Emergent stories are unpredictable, and that's part of the joy of it. But if you have specific story beats that you have to hit, then you either have to hope they happen randomly, or you need to herd virtual cats to make them happen. A planned story means we're looking ahead, sometimes far ahead, to make sure that certain story requirements can always be met. The most common way to plan a story is by hand, when you're designing the game. Scripts for AAA story games routinely exceed the length of the Bible these days, but they're still limited to what the designers can imagine in advance, however cool those might be. If you want to plan and replan your story at runtime, you need some kind of algorithm. By the way, these pictures you don't recognize are a couple of prototypes we built where the story is planned and replanned by an algorithm while the game is running. Planning means your story and your characters are anticipating a future sequence of events. You might only look one event ahead, or characters might have a script or behavior tree that forms a plan of several events. We call that reactive planning. The alternative is a search algorithm that considers all possible event sequences of any length. That's what I'm talking about today. Search is the most flexible kind of planning, but it's also the most expensive because there's usually billions, trillions, even infinitely many sequences that could be generated. By the way, a large language model is sort of doing reactive planning because it's mostly reasoning about the next word or event, though it can maintain some long-term reasoning in its context vector. I'm not really going to say much about LLMs in this talk, but I'll come back to them a little at the end. Remember, we're making stories out of events, which are about one sentence of content. An event has preconditions that have to be met before it can happen, and effects which change the world state in some way. In storytelling parlance, you might have seen these called storylets. They're pretty much the same thing, though depending on the system, storylets might be more like a scene than an event. A planner is an algorithm that starts in the initial state of your story world. It finds all the events whose preconditions are met, and simulates what the world would be like if you did those events. Then from those states, it finds all the events that could happen next, and it simulates those, and so on until we find a state where the story is over. Usually that means the player died or achieved their goal. So a planner considers everything that could possibly happen and chooses one particular plan that makes a good story. There's two ways you can use a planner to write and rewrite a story. The first is to use what we would call a deterministic decision process solver, or a classical planner. Mark Cavazza and his academic descendants have built a number of cool interactive story games this way. Classical planning algorithms represent events as having simple preconditions and effects. You start in the initial state, and it finds a sequence of events that achieves the goal. The nice thing about this approach is classical planning algorithms have been around since the 1960s, and every year cool researchers find new ways to make them faster. The downside is you have to write a lot of story context into the preconditions of your events. So for example, I might say that only rogues can steal things, and they only steal items that they want. The other option is to use specialized planning algorithms that have some knowledge of story structure built in. That's what I'm covering in this talk. The cool thing about a story planner is that you just write the basic preconditions of an event. It's up to the planner who can steal stuff and what they can steal. The algorithm has to look at the context of the event to figure out when it makes sense and when it doesn't. This saves you some effort, and it adds a lot of flexibility to your story, but it means the algorithm needs a model of what counts as a good story. In other words, a classical planner can put your Lego bricks together in any way they fit, so it's up to you to make sure your Lego bricks always look good no matter how they are assembled. A story planner will only put the bricks together in a way that makes sense, but this means they need a definition of when a story makes sense, and that's pretty complicated. This talk is about the last 25 years of story planning research, where we've been asking the question, how do you represent a story on a computer? We start in 1999 with this paper by my PhD advisor, Michael Young, where he suggests using a planning algorithm to write and rewrite the story in a game. A classical planner will generate every legal sequence of events which can be executed to get you to the end condition of a story. The trouble is that lots of plans aren't good stories, as we're about to see. In the next part of this talk, I'm going to show you some definitions for a story, followed by examples of how they don't work. The best part of that 1977 paper by Meehan is the misspun tales, where he lists some of the unexpected and funny outputs from his system. But that's how science happens, right? We come up with a definition, we try it out, sometimes it works, most of the time it just shows us new problems, and those problems motivate the next steps in the research. Here's a simple story from one of the prototypes we built. Your grandmother is sick, she gives you her very last coin, and you set off on a quest for some medicine. Thankfully, there's a merchant at the market who has some for sale. If you let a classical planner write your story, you might get something like this. The merchant walks to your house and hands you the medicine. That's a sequence of events that ends in success, but it doesn't really make sense. Merchants don't magically know what you want, and they don't usually give stuff away for free. The first story planner was developed to fix this kind of problem. Its big feature was intentionality. So instead of just having a story-wide goal, this planner also tracks the goals of each character. This narrowed down our definition of a good story. A good story is still a legal sequence of events that achieves the story's goal, but now every action also needs to contribute to achieving some character goal too. So now we've ruled out the merchant donating the medicine, but we can still tell the story where you go to the market and buy it. We can generate a story forward one event at a time, but intentions get propagated backward. We can simulate the player walking to the market, but we're not sure why. Then we can simulate buying the medicine, but we're not sure why. When we finally simulate the player returning home, we see that his goal is achieved, and this also explains the other actions that he did that contributed to the last event. We can also explain the merchant's decision to sell the medicine by her desire for money. So this meets our definition of a good story because it's a sequence of events that achieves the story goal, but we can also explain why every character did what they did based on their goals. Trouble with this first story planner was that it didn't allow character plans to fail. Imagine our story world also had an armed bandit. On your way to the market to get the medicine, the bandit finds you and steals your money. Stories usually revolve around some kind of conflict, so this seems like the kind of story we'd like to tell, but we can't because we don't have an explanation for why you would want to walk to the crossroads. The Glaive story planner fixes this by adding support for conflict. We're still generating our story one event at a time from start to finish, and we're still propagating explanations backward. The bandit robs you because they want your money, and they walk to the crossroads so they can rob you, but we can't come up with an explanation for why the player would walk to the crossroads. It might be the right thing to do for the story we want to tell, but it doesn't make sense to say you walked to the crossroads so you could get robbed. Actually, the reason you walked to the crossroads was because you were hoping to continue on to the market to buy the medicine. But that plan got interrupted. Even though it didn't happen, we can still use that plan as an explanation for your action. Remember, a planner is generating millions of possible stories before it settles on one. All those other stories that it didn't use aren't just wasted effort. They're actually a useful database of other possible stories that could have happened instead. So Glaive's definition of a story is a little broader. Instead of saying that actions only make sense when they're part of a character plan that works, we relax that a little and say that an action makes sense if there exists a story where it makes sense, even if that isn't the story you actually end up telling. We could have told the story where you walk to the market and buy the medicine. We could have told the story where the bandit robs you. We settled on the robbery because it's more interesting, but the fact that the other story was possible lets the computer explain why you were willing to go to the crossroads in the first place and how this robbery story still makes sense. Alright, we've made some good progress, but we're still generating a lot of misspun tales. Here's another one. Suppose there's a guard stationed at the market whose job is to punish lawbreakers. You're on the way to the market to buy some medicine when you get robbed by the bandit, then suddenly the guard comes charging in from off-screen to slay the bandit. This doesn't really make sense since the guard wasn't around when the theft occurred, so how did he know about it? The problem is that planners assume full observability, which means everybody knows about everything accurately as soon as it happens. That's not how most stories work, so we developed the Saber Story Planner to reason about character beliefs. Saber broadens the definition of a story to reason about plans that characters think are possible, even if they really aren't. So now, when we're trying to explain why a character does something, they have to have a plan they think will work to achieve their goals, based on what they know and have observed. But we're not done yet. Say you're on your way to the market and you get robbed by the bandit. The guard won't come running anymore because he doesn't know about the robbery. But what does the bandit do next? She thinks, hey, I know where I can steal some more stuff, and runs off to the market to rob the merchant. So the guard still gets her anyway. The problem here is the characters are thinking about ways to achieve their goals, but they're not thinking about all of the ways things can go wrong. The bandit isn't anticipating what the guard will do when she shows up at the market. We fixed this by introducing a simple model of 3 basic emotions. Hope means finding a plan to achieve your goals. That's what we were already doing in the previous planners. But now we can also reason about fear, which means imagining a plan other characters might do that will be bad for you, and relief, which means a plan that prevents a fear from happening. This paper also defines several other emotions as well as personality types. So a risky bandit might go for a second score in the market despite the guard, but a careful bandit would avoid the market. We're broadening the definition of a good story again to say that characters should only form plans they believe will lead to a positive emotion, like achieving a goal or preventing a goal from being thwarted. So now the bandit won't go to the market because she doesn't want the guard to mess up her goal of being alive. This last misspun tale is an all-time favorite of mine. We originally designed the guard in this game to be hungry. We imagined ways you could use that to get him to leave his post or entice him with poisoned food, but every time we tested our game, we'd show up at the market and the guard was already dead. It turns out that while we were on the way, the guard would steal food from the merchant, eat it, and then, because he had broken the law, attack himself. All of these actions make sense according to our model. He steals food because he's hungry, he attacks himself because he's a criminal, but the story as a whole doesn't make sense because he's not reasoning about the relative importance of his goals. Our latest paper, that we're presenting in a few weeks, narrows our definition of a good story back down to only consider plans on each character's Pareto front. A plan is on the Pareto front when there's no other plan that is better in some way without also being worse in some other way. To use a metaphor, suppose a character told you that they love pizza and pepperoni is their favorite. You go out to a pizza place for lunch and they order a slice of cheese. Does that make sense? Well, they love pizza, so in that way, ordering cheese makes sense, but they like pepperoni more, so ordering cheese doesn't really seem realistic when they could have just gotten pepperoni. Ordering pepperoni is strictly better, so it's on the Pareto front, and ordering cheese is not on the Pareto front. But suppose you heard there's a listeria outbreak affecting pepperoni. Now, ordering either slice is on the Pareto front. Pepperoni is better, but cheese is safer. In other words, when we ask if an action makes sense, we have to consider the other choices a character could have made instead. A plan only makes sense if there was no other plan that was better in one way without also being worse in some other way. So that's the current state of the art for our story planning algorithms. In summary, a story planner is a search algorithm which considers every possible sequence of events until it finds one that achieves the story's goal, but also for every character who takes an action, the character believes that action is possible, believes it's going to trigger a positive emotion, like achieving a goal or preventing a goal from being ruined, and there's no other plan they could have picked which is better in one way without also being worse in a different way. I've said a lot about planning, but what about replanning? Well, if you can quickly plan a good story, then you can just replan it when the player does something unexpected. If a player is about to do something that's going to make telling the story you want impossible, you stop them from doing it. We call that intervention. Ideally, you just let the player do what they want and replan the story around that new action. We call that accommodation. There are some fancier methods to make sure you don't paint yourself into a corner in these papers if you're interested. Alright, the last question that I don't really have time to go much into is whether we can do story planning fast enough to be useful at runtime. That's probably our biggest challenge. For non-trivial stories, we probably need to consider billions or trillions of event sequences to find one that meets all those criteria that I just listed. Currently, we can generate stories on the order of maybe 5 to 10 events depending on a lot of factors. We've done a lot of research on how to speed up story planning. One is fancy heuristic search. If you want to do something better than just breadth-first search, like say A*, you need a heuristic that can quickly guess how many more events your story needs before it's complete. In the Glaive paper, we developed a heuristic that quickly generates a sketch of what it thinks the rest of the story looks like, and uses that sketch to guide the search. We can also use fancy search methods with or without heuristics. For example, we might only allow events that involve a person, place, or thing that the player has already seen, which prevents the algorithm from wasting a bunch of time thinking about unknown off-screen events. We can try to only build plans where each previous event's effect satisfies the preconditions of an event after it. We can also reason about which people, places, and goals are currently salient in the player's working memory, and only allow events that involve those salient story elements. And finally, you might think that large language models would be good at guiding a story planner. They don't actually have to write the full story, just make suggestions for which event sequences will probably be good ones. Surprisingly, they're actually not better at this than older, simpler heuristic methods, or at least GPT-4o Mini wasn't. Language models are pretty good at open-ended storytelling, but they really struggle with long-term story planning, though that's starting to improve a bit with the so-called thinking models. I didn't talk much about LLMs because I wanted to focus on the definition of a story, and it's hard to get an LLM to follow a formal definition. But if you're interested in using LLMs for planned stories, you should start by checking out this paper for an example of the hilariously misspun tales you get when doing long-form storytelling with an LLM. There has been some cool work on getting LLMs to plan stories better by making them first generate and fill out outlines. Also, Mark Rydell's research group at Georgia Tech has done a lot of cool work on using LLMs for structured storytelling, like this paper on getting an LLM to do story planning. Despite the speed limitations, story planning has allowed us to make a few cool research prototypes. Our most recent one was a virtual reality police de-escalation training simulation. A training simulation is a great example of when emergent storytelling isn't enough. We have specific content that we need the story to include, and we need to make sure you get a good ending when you do the right thing, and a bad ending when you do the wrong thing. We need you to understand why the wrong thing led to the bad ending, so we actually want a fully deterministic story with no randomness, because we want you to replay it, intentionally do something different, and see how that leads to a better ending. We need our storytelling engine to look ahead and make sure it's always possible to tell the kind of story that we want to tell. We want the non-player characters to reason about hope, fear, relief, and we want them to choose the best available plan. Is a training simulation a roguelike? Well, it's meant to be repeated, and it has permadeath, but not much in the way of level generation. Come chat with me if you want to fight about this during the break. Okay, so this has been a very quick summary of the last 25 years of history on automated story planning for event-level interactive stories in games. To sum up the big lessons I've learned in my career, I think story planning is really neat because it lets you look ahead to guarantee the story you want to tell is possible. However, giving the algorithm a good definition of what makes a reasonable story is real complicated. One of the reasons it's so complicated is because storytelling is non-Markovian. That means you can't reason about whether an event makes sense just by looking at the current state. You usually need the whole sequence of events, the whole story, past and future, to decide whether an event makes sense or not. You can't just say whether an event contributes to a character's goal unless you know what they did before and what they're planning to do next. And if that wasn't bad enough, sometimes you also need to know all the other things that could have happened instead. To know if a plan is the best one for a character to choose, you have to look at all the other things they could have done instead. We can only judge the quality of a story relative to the other stories we could have told. Generating and checking all these event sequences is really, really expensive, even if you use fancy search techniques. Still, given how successful human story planners are at telling interactive stories, I'm optimistic that eventually we'll see some really cool, planned, interactive story experiences in video games, maybe even in a roguelike. Thanks for listening. Most of the papers I mentioned in this talk are on my website, if you're the sort to read academic publications. If you're a programmer interested in playing around with this stuff, the source code for our Saber story planner is on GitHub. And finally, thanks to the U.S. National Science Foundation and various parts of the Department of Defense who have funded this research over the years.